Hello and welcome to this section of the chemistry tutor. In this section we're going to switch gears a little bit. We've talked in the last several sections about acid-base reactions and doing calculations with what we call titrations when we bring acids and bases together. Now we've talked about different kinds of acids. We've talked about the strong acids and the weak acids. We've talked about the strong bases and the weak bases. And most of all, I think up till now, you've probably noticed that all of these acid-base reactions occur in solution. In other words, they occur in water, basically. And that's super important because most of the planet is water, most of your body is water, and so lots of interesting chemistry happens in water solution. And acids and bases are a part of that. It's really important. Now, what you've probably noticed up till now is that with these acids that go into solution, they dissociate, they break down into their ions, right? And then you also probably notice that these bases go into solution and they dissociate into their ions. And so we say, okay, the hydrogen ions from over here combine with the OH, the hydroxide ions over here, and they form water, right? So that was happening over and over again when we did some of these chemical reactions before, right? But the point is that the reactants, the acids and the bases, for the most part, always dissociated in water, which means they break down into these ions, and so everything can mix into this nice soup and the chemistry can happen, right? What we're going to start to talk about here is start to change gears a little bit. It turns out that not all ionic compounds actually dissolve in water. I mean, I think you can imagine lots of things that don't dissolve in water. You know, put a block of wood in water, it doesn't dissolve, right? So there's lots of things, lots of chemicals that if you pull off the shelf and sprinkle them in water, they're not going to dissolve. They'll just float, they'll sink to the bottom, but that's going to be it. They're not going to actually disappear and dissolve and dissociate. So those things that actually just sit there and don't do anything, if you have a chemical reaction between two entities, all right, and some of the products are dissolved, then you're not going to see them. But if you have a chemical reaction between two entities and one of the products kind of forms, but the product doesn't actually dissolve in water, then what's going to happen is you're going to start to see that product kind of appear before your very eyes, and it's going to sink to the bottom, right? And so it's important in order to be able to predict what's going to happen with reactions to know which compounds are soluble and which compounds are insoluble. It means they don't dissolve in water. And what we're going to do is build a chart here of guidelines to teach you when you can predict if a compound is going to dissolve in water or not. If it's going to dissolve, we call it soluble. And if it's not going to dissolve, we call it insoluble. And this is going to be important in a few sections, well actually in the next section, when we begin to predict reactions. So again, in this section we're going to give you some guidelines. I'm going to teach you how you can predict if a compound is going to dissolve in water or not. In your textbook, whatever book you're using, there should be a chart very similar to what I'm going to put on the board. It may be organized different, it may look a little different, but it should have basically the same information to let you predict if something's going to dissolve or not. But I want you to keep in mind the roadmap where we're going. You know, if you mix, an acid and a base, they're both dissolved, and the products are all dissociated as well. So you don't see anything necessarily happening. It's just a clear solution. But if I take any two clear solutions off the shelf in a chemistry lab and mix them together, I may get a chemical reaction where one of the products, I might get a reaction where one of those products is not soluble in water. And if that's the case, then it's going to kind of come out of solution as a little solid and sink to the bottom of the test tube or something like that. That's called a precipitate. So in the few sections, next section on, we're going to talk about precipitation reactions, where we mix two things and we're trying to predict if something's going to settle out of solution or not. So they're actually some of the coolest reactions in chemistry, especially when you get to your chemistry lab when you can actually see them. It's just kind of neat to mix two clear liquids together and get a nice, pink solid or something like that settling to the bottom of the test tube. So that's what we're going. Let's figure out how we can predict if something's soluble or not, and then when we get to the next section, we'll start to use this knowledge to predict if a precipitation reaction is going to happen or not. So let's put this chart on the board. One more thing I'll say real quick. I could easily just put this whole thing on the board and tell you, hey, this is it. We'll go write it down. But I really do think there's some value in me writing it out and talking about it as we go. I think there's just something about a blank marker board, and then you kind of see it slowly become filled up that is a little more approachable than if you crack open a chemistry book and see a giant table, because this table is kind of lengthy. But let's go ahead and do it one step at a time, and I think you'll agree that it's definitely not hard to understand. So what I'm going to start out by saying is compounds that are soluble. Compounds that are soluble. All right, so there's some general guidelines, and of course there's always exceptions. So I'm going to give you some of these exceptions. There's always going to be some crazy exception, but these are guidelines, right? These are going to cover you 99% of the time, kind of thing. All right, so when I say something soluble, that means it dissociates and dissolves in water. So one good example is nitrates. And just to remind you, a nitrate compound is anything with an NO3 ion, which has a charge of -1. That's what this means over here. So, sodium nitrate, calcium nitrate, things like this. Anything with a nitrate is going to basically, in general, dissolve in water. Okay? Acetates, which are things with a CH3COO with a negative there. This looks a lot like acetic acid, right? If you stick an H at the end here and it bonds with hydrogen, we call it acetic acid. But in general, you could have sodium acetate. You could have magnesium acetate. You could have lithium acetate, things like that. These things are going to be soluble in water. Perchlorates. A perchlorate is ClO4. So chlorine, oxygen, ClO4 with a -1. So again, sodium perchlorate, things like that. They're going to be dissolvable or soluble in water. Chlorates, ClO3 with a -1 charge. Anything with a chlorate at the end is going to be dissolved in water or be able to be soluble in water. And then here I have a large class. You'll see what I mean in a minute. Group 1A metal salts. And what I mean by that is, if you look in the periodic table, we talked about the periodic table a long time ago and how it's organized. On the left-hand side of the table, you've got that first kind of column there. That first column is what we call group 1A. Those are things with like lithium in there. Those are things with sodium in there, potassium in there, ... You just look at that column. What I'm trying to say when I say group 1A metal salts, what I'm saying is, you know what a salt is. It's when you combine something from the left hand side of the periodic table with something from the right. So if I say sodium chloride, for instance, sodium's on the left, chlorine's on the right, that's a salt. Sodium chloride, we know that's soluble in water. Lithium chloride would be soluble in water. Potassium chloride would be soluble in water. There's other things you can combine with on the right-hand side of the periodic table. This combined with something like a bromide, lithium bromide, sodium bromide, potassium bromide, those are forming different kinds of salts. When they involve a group 1A metal and they make a salt, they're going to be soluble in water. So this one right here is a huge class of compounds because group 1A is a large list, and you can make a salt with lots of things on the right-hand side of the periodic table as well. Finally, this is the easy list here. Ammonium salts. Don't forget, ammonium is NH4. It's got a positive charge. So something like, and when I say salt, it means it combines with something on the right-hand side of the table. So ammonium chloride, ammonium bromide, ammonium fluoride, things like that. Those are going to be soluble compounds. So this is the easy list because there's no exceptions really. I mean, I'm sure you could find some exceptions if you dig hard enough, but as far as things you're going to run into in a common chemistry class, this is going to be a great list of things that are soluble in water. So when you're trying to predict reactions later on and you're trying to figure out, hey, is this soluble or is this going to form something that settles out of solution, then you just look at this list. And this is the easiest one to kind of contemplate. Now, under that, we're going to get into some cases where there's a little more exceptions. So these are compounds that are very nicely soluble, like super good soluble, super nicely soluble, like sodium chloride, things that dissolve really readily. Next, we're going to have compounds that, erase this, that are mostly soluble. So in other words, these are soluble compounds, so they do dissolve in water, but just maybe not quite as rapidly or as vigorously or as readily as the first list. All right, so they dissolve, but they don't go crazy and dissolve, instantly, kind of thing. What are we going to have here? Let's do it the same color. Okay, so here you have your chlorides. And these are compounds that have a chlorine. You know, chlorine always wants to form a -1. I'm putting the charges here so that you can, as you're looking at the compounds, you'll have that as a reference. But basically anything with a chlorine at the end of it, like you know, potassium chloride, things like that, those are mostly soluble. But I'm going to get to some exceptions here and show you some exceptions here in just a second. So for now, let me just go down the list. If I have my chlorides, I have my bromides. Bromides are anything with bromine at the end. Br also likes to form a -1 ion. And then I've got my iodides. And these guys like to have iodine, which also likes to form -1 ions at the end. Now, these guys here are what I'm saying mostly soluble. In general, if you take something like sodium, like, you know, potassium chloride or potassium iodide or whatever, it's generally going to dissolve in water, but it's mostly soluble. It means that it is going to dissolve, but just maybe not quite as crazy as some of these guys are just going to instantly want to dissolve. But there are some exceptions, so I'm going to draw a curly brace here, and I'm going to say except with lead, which likes to have a 2+ ion, silver, which has to like to have a +1, and mercury. This guy. So what I'm trying to say here is that the chlorides, the bromides, and the iodines are mostly soluble, so you can pretty much count them as being soluble compounds, except when they're combined with these. So silver chloride, for instance, would not be soluble. Lead iodide would not be soluble. You know, lead bromide would not be soluble. So things like this. These guys, if you have a reaction that forms silver chloride, then the silver chloride is going to form and it's going to settle to the bottom as like a solid powder or something like that. It's not going to stay dissolved in the solution. So that would be an example of what we're going to talk about later, called a precipitate. Something precipitates. Think about that word, you know. This situation was terrible. It precipitated, you know, bad events. You know, you can kind of make up sentences even that use the words precipitated. To precipitate something is to make something happen, to cause something to happen. So when something precipitates out of solution, it literally just settles out of solution and just comes to the bottom. So these are one nice class of exceptions. Now let me give you one more important one that you'll definitely run across. Here you have your sulfates, which are anything that like to have SO4 at the end. And of course, sulfate is a -2 ion, polyatomic ion. And there are exceptions here. So let me draw my curly brace here and I'll say except with strontium, which likes to form 2+, barium, which likes to form 2+, lead, which likes to form 2+, and mercury, which likes to form 2+. So in other words, most sulfates are soluble in water, you know, potassium sulfate, you know, lithium sulfate, sodium sulfate. Those are pretty much going to be soluble. I say mostly soluble just to let you know that it's not as readily soluble, but it is going to dissolve in water. Anything in this category, when you see mostly soluble, you can count on the fact that it will go ahead and dissolve in water, just maybe not quite as rapidly as some of these up here. But if you did strontium sulfate, that's definitely not going to dissolve in water. Lead sulfate, you know, mercury sulfate, things like that, that's just going to fall to the bottom of the test tube. It's not going to dissolve at all. Let's go to our last class, and then this chart will be over. So these are going to be compounds that are insoluble. Okay, compounds that are insoluble. And I promise you, we're almost done here. So what do we have next? We have carbonates. Okay, and these are compounds that have CO3 at the end, and they like to have a -2 charge. These are polyatomic ions you've probably heard of before, saw in your book. Hydroxides, which you probably recognize because we've been doing that a lot with acids. These are OHs, negative. And I'm going to come back and talk about the hydroxides a little bit here in a second because you're probably wondering why they're insoluble. We'll talk about that in just a second. We have phosphates. And these guys are PO4 anything with PO4 at the end, and it likes to have a -3 charge. And then we have sulfides, which are anything with S at the end, and they like to have a charge of -2. Now, these guys in general, the carbonates, the hydroxides, the phosphates, and the sulfides, in general, they are insoluble. They're going to fall out of solution, except there's a fair number of exceptions here that are going to cover some of these things you've probably seen before. So I will say except. With ammonium, NH4, and group 1A metals. Group 1A metals. And let me go ahead and just kind of draw a little line here, and let me write it in purple. I'm just going to write another little note. I'm going to say note hydroxides and sulfides with Ca2+, strontium 2+, barium 2+, are moderately soluble. So I have good news and bad news. I mean, the good news is, or I guess the bad news is, it's a long chart. I mean, you can see why I didn't just want to just write it down and say, hey, go memorize this, because you don't have to memorize it. Memorizing it's not important. What's going to end up happening is you're going to remember some of these compounds that are soluble and some that aren't just by using them so much. But definitely don't try to memorize the chart. The bad news is the chart's kind of long and there's lots of exceptions. The good news is this one little page is going to cover you for most reactions you're going to cover in a chemistry course. You should have in your textbook, whatever book you're using, a chart, a solubility chart that looks something like this. It'll have, you know, what's insoluble, what's moderately, and what's fully soluble. And you'll have exceptions. And you might even have slightly different things listed, like all of these should be on there, but your book may have a couple of additional things listed here and tell you if they're soluble or not. This one is going to cover you for most cases. It's going to cover you for most cases. So let's go and talk about these insoluble compounds here. So in general, anything with a carbonate, a hydroxide, a phosphate, or a sulfide are going to be insoluble unless it's combined with ammonium. So if it's ammonium carbonate, if it's ammonium hydroxide, if it's ammonium phosphate, then it's going to go ahead and dissolve in water. Or if it's combined with group 1A metals. Remember group 1A metals, we talked about that actually up here, group 1A metals. These are lithium, sodium, potassium, everything in that very first column of the periodic table. On the very left-hand side, those are the 1A metals. So when you have sodium, for instance, sodium is in a group 1A, sodium hydroxide, that's an exception. It's very soluble. So when we're doing acid-base reactions, we did sodium hydroxide a lot. It's cheap chemical, very readily soluble. It's a great electrolyte. It's an exception to this general rule that most hydroxides are not soluble. So sodium hydroxide is soluble because of the exception. Lithium hydroxide is soluble. It's an exception. Potassium hydroxide, it's an exception because they're all group 1A metals that are bonding there. And then same thing is true of these guys here. You know, in general, a sulfide is not going to be soluble. But unless it's an ammonium sulfide, or if it's a potassium sulfide, or if it's lithium sulfide, then it's an exception. And finally, I want to explain this note at the bottom. Hydroxides and sulfides with calcium, strontium, and barium are moderately soluble. So what this is saying is hydroxides and sulfides, you know, usually what I'm saying here is that these guys, I've got the exception here, right? I've got the carbonates, the hydroxides, the phosphates, and the sulfides. They're not soluble unless this exception applies. This exception applies to all of these things. So the exception, you know, sort of like the big exception is this, you know, ammonium, you know, carbonate is soluble, ammonium hydroxide soluble, ammonium phosphate soluble, ammonium sulfide is also soluble. So this exception applies to everything here. So I had to add, or the books have to add another note, because for hydroxides only, calcium hydroxide is soluble, strontium hydroxide is soluble, barium hydroxide is soluble. Calcium sulfide, strontium sulfide, barium sulfide, they're moderately soluble. So it's giving you kind of an exception to the exception a little bit. This exception applies to all of them, And these are just giving you very specific examples because calcium hydroxide is something you run into all the time. Barium hydroxide is something you run into all the time. Those things are moderately soluble, even though if I didn't put this note here, then you would say, okay, hydroxides are not soluble. Is barium in this list? Okay, or is strontium in this list here? And you would say no. So then you would say, all right, well, strontium hydroxide or calcium hydroxide must be insoluble. Well, that's actually another exception. So everything on the left is the general rule. Everything on the right is a general exception. You're never going to memorize the exception, so don't try. It's a chart, right? It's a chart, so use the chart, okay? If your teacher lets you have a little cheat sheet or something like that, or if they're providing a chart, at least you'll know how to use it. So what we're going to do is I'm going to give you a compound. We're going to write them on the board, just a simple compound, and you're going to use the solubility chart that we just created to figure out if it's soluble in water. Now, it doesn't really so much matter if it's mostly soluble or whatever. I mean, that's kind of like different grading of how soluble it is. Mostly what you're interested, is it going to dissolve or not? Okay, period. Because when we get to precipitation reactions, all we're going to care about is if it dissolves or if it doesn't. So in the chart, I've broken it into really soluble, mostly soluble, and insoluble. But for the purpose of when someone asks you, hey, is this soluble or not? You don't really care if it's mostly soluble or fully soluble. You just care if it's soluble at all, or if it's insoluble. So let's go and do one of these guys. What do you think about sodium bromide? Is it going to be soluble or not? Sodium bromide. So the way you do it is you go up here and you look for a bromide, or you look for something with sodium. So it's not a nitrate, it's not an acetate, it's not a perchlorate, it's not a chlorate. Group 1A metal salts. Sodium is a group 1A. It's combining with bromine, so that's something on the right-hand side of the table, and so that's going to form a salt, right? Sodium bromide then falls into this category right here of something that is soluble. So that's going to be soluble. Okay? So this is how you use the chart. What about barium sulfate? Barium sulfate. Okay, so you just go down the list, you get down here, it doesn't really fit into acetate, perchlorate, ammonium salt, or anything like that, so you go down here. Is it a bromide? Is it a chloride? Is it an iodide? Okay, it's a sulfate. So I found the category. Most sulfates are actually soluble, unless it's combined with strontium, barium, lead, or mercury. So most sulfates are actually soluble, but this one is combining with barium, so it's barium sulfate. This is an exception. So it's not mostly soluble, it's just not soluble at all. So this guy is insoluble. It doesn't dissolve. So if you had a reaction that produced barium sulfate, it would just sort of suddenly appear in the beaker and settle to the bottom. What about potassium? Potassium carbonate, CO3. Down here, potassium carbonate. So you look at your list, you say, okay, I found the carbonates. Most of these guys are not soluble at all, but it says except ammonium combining with it or group 1A metals. You look at what's combining with it, potassium is a group 1A metal. That's on the first column of the periodic table. So you come down here and you say, well, most carbonates are not soluble, but this one's combined with an exception, so it is soluble. So, soluble. Okay, what's next? I have silver chloride. Okay, silver chloride. So I go up here. It's not a group 1A metal salt. Okay, compounds that are, okay, so I've got chloride. I found the chlorides right here. Most chlorides are actually soluble to some degree, except when it's combined with lead, silver, or mercury. And this is silver chloride, so it's not soluble at all. It's insoluble because it's an exception. So this is insoluble. All right, next, we're just going to do a few of these guys. NH4SO4. So this is ammonium sulfate. So I come down here, immediately I hit ammonium salt, all right? So ammonium salt might indicate that it's soluble, but then I go down here just to double check and I get to sulfates. Sulfates are also soluble. Unless it's combined with one of these guys, and it's combined with an ammonium ion, so it's not one of these exceptions. So if you go by this guy up here, then it's soluble because of the ammonium listed here. If you go by this guy here, it's also listed as soluble, so it's going to definitely be soluble to some degree. Okay, there you go, soluble. All right, the next guy on the list is BaCl2. Okay, so barium chloride. So you come up here, you don't see anything here, you get to chloride. Most chlorides are soluble unless they're combined with one of these, which is not barium. So since most chlorides are soluble, it's not an exception, soluble. Okay, and let's go down here to our final kind of problem, and then I'll switch gears a little bit. I've got lead nitrate. PB, lead nitrate. All right, so we go up here, nothing down here, my nitrate, I look for my nitrates, and I see my nitrates way up at the top. Nitrates are soluble, so there's no exceptions to it, so it's going to go ahead and be soluble, so that's pretty easy. All right, now for the next one here, for the next batch here, I'm going to write down a couple of different compounds, and they're all going to be sort of similar, and we're going to circle the ones that are actually soluble by looking at our list. So it's basically the same sort of thing. So what if I had silver chloride, silver phosphate, and silver nitrate? Let's figure out and circle the ones that are actually soluble. We'll circle the ones in this list that are soluble. If there, maybe there's one, maybe there's more than one. So here we have silver chloride. So we come up here and we find the chlorides. These are soluble, but there's an exception, and it's combined with silver. So that's definitely not soluble. So we're not going to circle that one. The next guy on the list is silver phosphate. So we'll come down to phosphate. Here's phosphate, right? Here's phosphate. These are insoluble, right? They're insoluble. The exception is ammonium or group 1A metal. Silver is definitely not a group 1A metal. This note doesn't apply at all. So silver phosphate is not soluble either because it's in this bottom guy here. The last one we have is silver nitrate. So we go up, we see nitrates. Nitrates are basically always soluble, no matter what. There's no exceptions. So the only one in this list, silver chloride, silver phosphate, silver nitrate, the only one that's actually soluble is going to be this one in water. So if we have a reaction that forms silver chloride, it's going to sort of form like a little cloudy thing that's going to settle. If we have silver phosphate form, same thing's going to happen. And of course, if we form silver nitrate with some reaction, then no precipitate forms, everything stays in solution because the product is dissolved basically there. All right, and we'll do one thing here at the end. We'll have potassium chloride and potassium carbonate like this. Let's figure out which one of these are soluble, and we'll circle the ones that are soluble. So potassium chloride. So we'll go to chloride, which is here. These are soluble unless they combine with one of these guys, which potassium is not one of them. So it should be soluble. So this is soluble. And then we have potassium carbonate. So I come down to the bottom. Most carbonates are insoluble. However, there's an exception. Ammonium or group 1A metals combining with it. So this is a carbonate, all right, but potassium is a group 1A metal, so it's an exception to this guy. So instead of being insoluble, it actually is soluble. So if we have a reaction that forms potassium chloride, it'll be dissolved in solution. If we have a reaction that forms potassium carbonate, it'll be dissolved in solution. So we're not going to have precipitates formed for either one of these guys. Now, this pretty much covers the solubility rules. I want to go ahead and say, as a follow-up, let's go back down this list as practice. And let's go figure out, for whatever ones we've listed as being soluble, all the ones that are being listed as soluble, let's go write down really quickly what ions are going to be formed when we get into solution. What ions are going to be formed when we get into solution. Because for instance, this guy is sodium bromide, right? It's soluble. So if we actually put that in water, what ions are going to form? Sodium, if you look at the periodic table, is always going to form +1 ions. And bromine, if you go and look at the periodic table on the right-hand side, it's always going to want to form negative ions. And I've taught you how to look at the periodic table in previous lessons in previous chemistry lectures, how to look at the table and figure out what charge it's going to want to form. The reason we're doing this now, predicting the ion charge, is because in the next couple sections it's going to be important when we write the net ionic equations to be able to put the charge. Also in the future when we do redox reactions, it's important to know what the charge on the ions are for that as well. So we're just getting practice here. So this is insoluble. It's not going to form any ions. So this is going to bond together and settle out of solution. So that doesn't apply. This guy is soluble. So what do you think it's going to form? Well, potassium likes to form +1. So we're going to have +1. Notice it's K2. So we're just going to put the 2 in front just to say, hey, there's 2 moles of potassium. For every 1 mole of this stuff, you're going to get 2 moles of potassium out, so we're just going to stick a 2 in front there just to denote that. But the main thing is that it's +1 ion forming. And then we have a carbonate, CO3. And if you forget, you can always look back at the chart I gave you. Carbonates always want to form -2. So you write it as 2 negative like that. So these are the ions that want to form. Silver chloride is not soluble, so it doesn't apply. Ammonium sulfate, we go and look and say, okay, it's going to break into ammonium and sulfate ions. So NH4 always wants to form +1 ions. We have 2 of these guys, so I'm just going to carry the 2 in front just to denote that if I have 1 mole of this dissolving or dissociating, I'm going to get 2 moles of the nitrate and only 1 mole of the sulfate. And sulfates, SO4, if you forget, go back to the sulfates, it wants to have a -2 charge, like this. So those are the ions that are going to form. Barium chloride, if you look at the periodic table, barium always wants to form +1 because it's in that first column. And chlorine always wants to form -1. But notice I have 2 chlorines here, so I'm just going to carry it and say I have 2 chlorine ions. I'm just writing these numbers out in front just to kind of match what the formula is here to keep track of everything. And then the lead nitrate, okay? This is actually an interesting one because most of the time lead wants to carry a +2 charge, but every now and then lead can have different charge, right? So how do you figure it out? Well, you can figure out what charge lead has here if it breaks down because of the chemical formula. I mean, if you think about it, if I have a 2 here, then if I do the crisscross backwards, that means there has to be a +2 here. And of course there's a 1 here, so the nitrate has to have a -1. So the lead has a charge of 2+, which is what it normally carries. You can kind of see that from the chemical formula here. The nitrate ion, if you forget, the nitrate ion is over here. Nitrates carry a charge of -1, so I'll put a -1 there. And since I have 2 nitrate ions, I'm going to put a 2 in front. So when this breaks down, I'm going to get, for 1 mole of this guy that breaks down, I'm going to have 1 mole of lead ions, and I'm going to have 2 moles of nitrate ions, and I've listed the charges here. So that is going to about do it for the section. We've basically introduced a table, which, you know, I don't know, maybe you have a different way of organizing it. Maybe your book has a fantastic chart that you like better. But I think this is a pretty easy way to look at it. I mean, it's got it broken down into these ions. I mean, is it a nitrate? Is it an acetate? Is it a perchlorate? Is it a chlorate? So on and so on. Is it a group 1A metal salt? So on. So you can easily figure out what's soluble. The compounds that are mostly soluble are listed with their exceptions. We've given you practice that. The compounds that are insoluble are listed with their exceptions, and we've given you practice with that. So we've practiced that with lots of different examples to figure out if they're insoluble or soluble. And for the ones that are soluble, we've practiced writing down what ions are actually going to be in solution, you know, after they dissolve and dissociate. And that's super important because what we're going to do in the next section is we're going to start to look at reactions that happen in solution. And I'll give you kind of a preview that when you're looking at reactions that happen in solution, if they're precipitation reactions, they're going to happen if one of these, at least one of the products forms something that's insoluble, because then it's going to combine and fall out of solution. So if it's forming something that's not soluble, we're going to easily be able to identify that as something that's chemically bonding, falling out of solution, and that's going to be a really important result. So follow me on to the next section where we'll talk about precipitation reactions. We're going to use this chart, so I'm going to leave this chart on the board. And I suggest that if you're taking notes here, it's up to you, but if you're taking notes here, to write it down yourself. But I'll definitely leave it on the board as we do our future problems. And what we'll do is we'll be looking at these reactions, figuring out what's going to form, what's going to be soluble, and what's not going to be soluble, and that's going to help us predict what's going to happen. and then we'll be going on from there and solving those problems, writing our equations down and doing our predictions there. So, hope you've enjoyed this section. Make sure you understand how to use this chart. You're almost guaranteed to see something like it on your test. Follow us to the next section where we do our precipitation reactions to see what's going to form, and more specifically, what's going to form a solid, insoluble thing that settles out of a solution in an aqueous reaction.